Welcome back, everybody. This is our video solution to problem 2 from Quiz 8, Fall 2023, Math 307, Linear Algebra at Cal State Fullerton. In this problem, we are given a vector space of continuous functions from the closed intervals 0 to 2 pi to the complex numbers. And this is a vector space under the usual addition and scalar multiplication of functions. So remember, this means that if I have two functions f and g, defined on 0 to 2 pi, then I can evaluate them at some point x between 0 and 2 pi by simply adding the values of f and g at that point x. And if I want to multiply f by some scalar and then evaluate some x, I just evaluate f at x and multiply by that scalar. Okay, and we want to prove that the following function, let's see, you're going to take two continuous functions f and g. We're going to multiply 1 over 2 pi by the integral from 0 to 2 pi of f times g bar. And we want to show that this function actually is an inner product on the vector space. All right, so in order to show we have an inner product, there are 4 axioms we have to check. So these are the inner product space axioms. So the first one is positivity. Positivity is the axiom which says that if we take the inner product, right? Of course, we're assuming it's an inner product when I say that. But if I look at this angle bracket f with itself, that this needs to be always at least 0. Okay. Now that can be a little bit challenging if you're dealing with complex valued functions. So we have to make sure, right, implicit in this, right, that we actually get real numbers as our answers. The second condition we need to check is definiteness, which says that, well, what if I take this product of f with itself and I get 0? This should happen if and only if f itself is equal to the 0 function. The third axiom is going to be what we abbreviated FAL, first argument linearity. And so this tells us that if I take f plus g comma h, then this should be the same thing as f comma h plus g comma h, right? Applying this function. And also if I multiply f by some scalar alpha, and then take this inner product with h, I should get alpha times the product of f comma h. Okay, and then finally the fourth one is what we called conjugate symmetry. And conjugate symmetry says, well, what if I want to try to flip this, right? Instead of f comma g, I want g comma f. And conjugate symmetry says, yeah, you can do that, but there's a cost. You have to put the complex conjugate. Okay. So we're going to check these 4 conditions. So let's start with, say, positivity. So with positivity, I'm going to be looking at f comma f, which is going to be 1 over 2 pi times the integral from 0 to 2 pi of f bar, right? Now the g is just an f, dx. Okay, and importantly, if I multiply a function by its conjugate. So what do I mean, of course, by the conjugate, right? Let's put that just over on the side here. If I have f bar of x, what I really mean is take f of x and then take the complex conjugate. So here when I do f bar, that would mean if I applied it to some x, I would be getting, right, f of x times f of x bar, which is equal to the square of the norm of f of x. Right? So this absolute values around f of x, when we're talking about a complex number, right? We don't really call it the absolute value anymore, but it still means kind of the same thing, right? It's the distance to 0, and then we'll square that number. So we can write this here in sort of the obvious way. We'll take the length of f squared, right? Meaning we evaluate f at x, take the length of that complex number, and square it. All right, so because, though, we are taking a length here and squaring it, this is now some real valued function, right? So this is a real valued function, which means when I integrate, I'm going to get a real number, right? So that handles at least the part where we need to make sure we're getting a real answer, right? Next, we need to make sure that it's actually a non-negative real answer. And this seems intuitively quite clear because we're integrating something which is a square, right? Squares are inherently going to be non-negative, right? How are we possibly going to get something which is negative out of it, right? And of course, that's exactly how integration is going to work, right? Since we know that the absolute value or the norm or the length, whatever, squared of f is at least 0, this implies that the integral from 0 to 2 pi of f, well, we'll put it in norm squared terms, that this is at least the integral from 0 to 2 pi of 0 dx. But this is just equal to 0. And of course, if we divide by 2 pi, nothing actually changes here. All right, so this gives us our positivity condition. All right, let's check definiteness. Now, here we're going to assume that 0 is equal to f comma f. But this means now that our 1 over 2 pi integral from 2 pi, and I'll just keep using this length of f squared notation, that means that this thing is going to equal 0. Okay, and again, intuitively, you think, yeah, like this thing is always at least 0, so if you get 0 and you add it all up, like it must be 0. But there's a little subtlety here, which is that it might be possible that the function itself takes on values that are greater than 0 without making the integral greater than 0. So let's just draw a quick picture of this. So maybe I was going to go from 0 to 2 pi, and if my function, right, was 0 a lot of the time, but then every once in a while it would hop up to some other value, non-zero. Well, the integral is still 0, but the function is not, right? Look, I have 4 points here, right, where the function is non-zero. So what I claim is that in general that could happen, but in our situation it can't. And that's because we know that the function f is coming from, well, the set of continuous functions from 0 to 2 pi to c. Okay, so why is the continuity useful here? Well, once you know that you have a continuous function and that there is, say there was some positive value, then there actually must be an entire interval where that function takes on a positive value. All right, so if this length of f squared evaluated, let's say at some point x, is greater than 0, then there exists an interval, let's call it, say, I don't know, a to b, containing x, such that the length of f of, well, let's just call it z squared, is greater than 0 for all z in AB. Right? Okay, well, once we know that, then we can break this integral up. All right, so let's draw another picture. Here's our 0 and our 2 pi, and somewhere in there we have a and b. Right? It looks rather large in this picture, but it might be quite small, but it doesn't even matter. The point is now, I can integrate from 0 to a. I can then integrate from a to b, and then I can integrate from b to 2 pi. Now, one thing we already know is that anywhere I integrate on this interval, my answers are going to be at least 0. We prove that in the positivity section. that means that, well, even if I'm 0 outside of AB when I integrate, and 0 here, I still get something which is non-zero when I'm integrating on A to B. Because from A to B, the function, right, length of f of z squared, is positive the whole way. So, since I know that if I integrate f squared on this interval, AB, and this is positive, and when I integrate on the other intervals, those are at least 0, then the entire sum, right, which is the original integral, this entire sum has to be positive. And that would violate our assumption, right? We actually know, well, okay, divide by 2 pi, that doesn't change anything. All right. Okay, so this implies that 1 over 2 pi times the integral from 0 to 2 pi of the square of the length of f dx is greater than 0, a contradiction. What did that contradict? It contradicted our assumption that the square of the length of f of x could be positive for some x. Right? Okay, so that tells us that f equals 0 on 0 to 2 pi. Okay, well that's a little bit of a harsh analysis for us, huh? All right, well we got 2 more to check. So let's look at number 3, the first argument linearity. And this should be substantially easier because it's just going to come from a well-known property of the integral. So if I have f plus g comma h, then this would be 1 over 2 pi times the integral from 0 to 2 pi of f plus g h bar dx. All right, but let's just distribute this h bar. I get fh bar plus gh bar. And now I know that if I have the integral of a sum, it's the sum of the integrals. So this becomes 1 over 2 pi, the integral 0 to 2 pi of fh bar dx, plus 1 over 2 pi, the integral from 0 to 2 pi of gh bar dx. But this first integral is precisely f comma h, and the second integral is precisely g comma h. Okay, so we have the additivity portion of first argument linearity. All right, now what if I had multiplied by a constant? Well, now I have 1 over 2 pi, the integral from 0 to 2 pi of alpha f h bar. But of course, I can just take this alpha and pull it all the way outside the integral. Write this as alpha times, I'll just put parentheses here, 1 over 2 pi, the integral from 0 to 2 pi, f h bar dx. And of course, this is just now alpha times f comma h. So we're really just using actually the linearity of the integral. Now you might be wondering, well, can't you do these both at once? What if we just did alpha f plus g comma h? Of course you can. I'm doing it separately for mostly pedantic purposes. All right, finally we need to check the conjugate symmetry. So for conjugate symmetry, we'll have to use maybe a lesser known property of integrals. So if I want to compute, say, fg and then, well, let's take the bar of it, right? Or here we wanted to say fg was gf bar, so maybe here we'll make this gf bar. So here we have gf bar, so this will be 1 over 2 pi, the integral from 0 to 2 pi of gf bar dx, and then we have to bar everything. Right? So there's gf underneath the bar, and then we put a bar. Okay, now, the bar of a product is the product of the bars, and 1 over 2 pi is a real number, so the bar of that is just what it is. Now I have the complex conjugate of an integral. Think of an integral, though, as it's really the limit of sums. And the complex conjugate is going to then play out over, it'll commute with those sums. And so this will actually be the integral from 0 to 2 pi of gf bar, and then we bar gf bar. But the bar of a product is the product of the bars. So this is 1 over 2 pi, the integral from 0 to 2 pi of g bar f bar bar. Oh, but f bar bar, right? You're taking the bar of the bar. That's just the original function. So this is 1 over 2 pi, the integral from 0 to 2 pi of f g bar, right? Of course, I'm going to swap the order here because now it's obvious this is f comma g. And therefore, we have conjugate symmetry. And therefore, this map we've defined is an inner product. And that's it. That's our proof. All right, everybody. Whew, that was a tough one, right? That's very long. We'll see you next time.